Hello everyone, I hope everybody's doing fine. I'm going to check my bearings here, make sure everything's working fine. Give me a second here. YouTube seems to have a problem, and I was going to complain about it, but somebody beat me to it. And so they said they're working on it. Whatever that problem is, it gives you an error of some kind. See if I'm okay here. I guess I'm doing okay. Okay, so let's get started. Until now I've been addressing the questions first and then doing the lecture. I think I'm going to switch that around. I think it's not good for people who just come to hear the lecture to have to wait till the end. So I'm going to switch them around. I'm going to do the lecture first, the questions later. If I can get to them, we'll find out how much time it takes, okay? Anyways, what are we going to do today? Well, we're going to do this gentleman. His name is Jim Al-Khalili, and he's supposedly a mathematical physicist, okay, which means he's not a physicist, he's just a mathematician. Actually, we call them mathemagicians. Okay, good old Jim, as we saw the other day, he's got an impressive resume, right? And he's supposedly a theoretical physicist, author, broadcaster, professor of theoretical physics, chair in the public engagement in science, blah, 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 blah. He's got a lot of stuff there, a lot of medals, okay? Been in a lot of wars. I guess he can't be in His Majesty's service if he's not born in England. I don't know what the laws say about that, but he's born in Baghdad, so I don't know if that, and he is a citizen of Great Britain, but then the question is whether he can be, knighted. I think he cannot, but I don't know this, okay? Anyways, because that's all he needs in his resume practically, okay? But we found out that good old Jimmy, he's actually a caricature of physics. Why? Because, and of sciences as well, right? Because he says an atom is mostly empty space. This is what he says. An atom is mostly empty space. Where did he get this? Well, he got it from good old Rutherford, right? And everybody just parrots that without understanding what they're talking about. Anyways, it turns out empty space is made of particles, according to Al-Khalili. And so, what does that mean? An atom is mostly made of particles? I don't know what that possibly can mean. They have a contradiction they got to resolve there. A particle can be at two places at once. Strong force is a bed spring that holds quarks and protons together. You can see it up there in the upper right-hand corner. He believes in spirits known as black holes and dark matter. He thinks they lurk in the darkness of dark energy out there in the middle of nowhere, okay? And there you see the black hole. Universe self-created when the concept energy spontaneously morphed into the concept mass. Okay, they call it a Big Bang. There you see a little GIF on that. And he says we wouldn't have computers or GPS if QM and GR, general relativity were wrong. Well, that's so misconceived. Shows that he doesn't even know he doesn't have a basic understanding of what science is. No, technology has nothing to do with science, and therefore technology is not a confirmation of the theories of quantum mechanics and general relativity, specifically the physical interpretations. And we're going to deal with that in a minute here, but I don't want to get too far ahead of myself. Anyways, today what is he going to talk about? Well, he's going to talk about Thomas Young's slit experiment, double-slit experiment. I think he performed it for the first time in 1801. 1802, I think he gave his lecture, and by 1803 he had done a couple of these experiments, I think. Anyways, Thomas Young wrote about this, okay, experiment that he did diffraction. And the only difference, I guess, between them is Young did it with waves, and that's 100 years ago. Today we do it, or at least, 200 years ago, what am I saying? And Al-Khalili does it today with particles. So, you know, I think I'm going to change his name to Alkali, right? Or maybe I should change it to alcohol or something like that. I don't know. You'll find that. You tell me today after today's lecture, okay? Anyways, Al-Khalili does it with particles, and he can't explain it with particles, although he claims that that's what he does. In fact, it starts with the boast, the claim of the Royal Institution, where he gave us talk, and the Royal Institution, a little church out there in England somewhere. So it starts out by boasting that Al-Khalili is going to explain the double-slit experiment. I had my hopes up. I said, finally someone who can explain the slit experiment. I waited all these years. Okay, and the title of Al-Khalili's lecture reads, I hope I got it right, it says, Double-Slit Experiment Explained by Jim Al-Khalili. Explained. Okay. Now, Jim does have a disclaimer there. He's got a little bit of fine print and says, if you can explain this using common sense and logic, do let me know because there is a Nobel Prize for you. That means he doesn't plan to use what? Common sense or logic. Then what the hell is he going to explain? I mean, if he's just going to describe, he should have used the word describe and not the word explain. And we see this over and over coming from mathematical physicists. They constantly talk about describing and not about explaining. What's wrong? The sound is too high? Sometimes it's too high, sometimes it's too low. Okay, let me get it a little lower. Let me know if it goes down, okay? Let's get this down to I hope that's better. Hello, hello, can you still hear me? Let me know if who said that? You sound like a Colombian. Okay, how do I sound now, guys? A little better? Let me know. I don't want to break your ears. Okay, I'll continue. Let me know if I'm a little too high on the sound. Still too hot. Get it down lower. How about now? No, still high, I think. I don't know, get it a little lower. Is that better? Hello, hello, hello. Now I've got the thing as low as I can get it. I can't believe that sometimes I get it too low, sometimes too high. Let's see. Let's try this. I'm checking the volume here. Hello, hello, hello. Still high. I can see it. I can see it here. It's extremely high. Last time nobody could hear me. Now, keep trying. Hello, hello, hello. Is that better now? I think that should be better now. You should be able to hear me just about right, I think. Okay. Thank you. I don't know what's going on. Last time it was low, I had to raise it. Now it's a little too high. Who understands this? Anyways, let me continue here. What are the problems with what Jim Al-Khalili says about the slit experiment? Well, the first thing I want to start with is with some of the problems that we have with mathematical physics. So let me go over the summary. Let me go over the summary of what I'm going to cover today and how with Jim Al-Khalili, where he's going to fail, okay? So this is going to be like a summary. I'm going to just give you a little introduction here on what he's going to be presenting. I want you to keep an eye out for these issues. These are the ones that underlie his talk, okay? And here it is. First one, mathematical physicists dismiss physical interpretations as petty philosophy. They say that doesn't belong in physics. So the question is, why did the mathematical physicists, okay, attempt a physical interpretation to begin with if that's just philosophy, if physical interpretations are not part of physics? Okay, why didn't he just stick to math? And the answer is there, because otherwise his math is irrelevant to the real world. It has no purpose. Okay, so this is the issue. The issue is that on the one hand, they dismiss physical interpretations. They say, well, that's philosophy. That's the philosophy of physics or the philosophy of science. And then they all try to go in there to the public to try to explain what they do in physical terms. Okay, and they make a big mess of it. It's all irrational. And then when you question them about it, they say, well, that's philosophy anyways. Science is math, not physical interpretations. Okay, so this is the issue. Keep that in mind, okay? And the first issue is that they cannot explain with math. Math exclusively a descriptive language. You can only describe with math. And if you can only describe, of course, you cannot explain. Now you understand why in the last 400 years they have converted science into math, into descriptions, and we have no explanation, no rational explanations today. None. Not coming out of the mathematical physics world. That's why they are not physicists, because we need to understand, you know, why the Earth doesn't fly out of the solar system. And they say it's warp time. And you say, well, that sounds irrational. And they say, yeah, we don't understand it either, but that's philosophy anyways. So don't ask that question, because you're asking the wrong people. You should ask the philosophers. What do? They send you to the mathematicians. They say, oh, they're the ones who know. They tell us. So that's where we got to run around, okay? Anyways, the physical interpretation part is inferred, and this is an important reason that mathematical physicists reject physical interpretations as a component of science. Mathematical physicists see it as an opinion, speculation, or belief. Okay, so because it's inferred, and they can't prove it, they can't tell you what's in there in that invisible world, and so they say, well, that's not science anyways. We have no way of proving it. That's their argument, in essence, okay? That's the first issue. Second issue here, rundown. Math phys simulate everything with particles. That's the problem. For the last 10,000 years, they've been using particles. Even when they use waves, they're doing particles. Because what is a wave? It's a up and down the oscillation of particles. Some say it's the oscillation of nothing. Fine, that's even worse. But they've always used particles. And this site is the first one for the first time that we have a different proposal than waves or particles, guys. And obviously it's not wave packets or none of that nonsense from quantum. Okay, simulating the invisible atomic and subatomic world with particles inevitably leads to paradoxes. And instead of saying, well, we got a paradox, we have a problem. No, instead it's like Niels Bohr once said, oh, we've reached paradox. Now we have a chance of making progress. So they boast about it. They think it's good. Okay, and they mathematical physicists, they twist this around in their favor and proudly call them dualities. Okay, so if light is both a particle and a wave, you know, if you can't, what other dualities are there? Well, they have tons of them. You know, I mean. Really, they're all over the place, and a lot of them just have to do with interpretations, all on the basis of particles. That's the issue. That's the main one, the duality of wave-particle duality. Okay, they don't see dualities as defeating their theories, but rather as quirks of nature, Mother Nature playing incomprehensible tricks on them. So the question is, you know, I'm not a great fan of Karl Popper. I think what he said is nonsense, okay? But these people believe in in Karl Popper. And Popperian falsifiability, why didn't they apply this principle just now when they needed it the most? They needed it here to reject the particle hypothesis. Because if you cannot explain anything, absolutely anything, with particles, with discrete particles, then this is the moment that you have to apply Karl Popper and say, look, we can't explain the slit experiment. We can't explain polarization. We cannot explain, how the atom works. In other words, how the electron gets bound to the proton. That's the main issue, right? How does the electron stay faithful to the nucleus? They can't explain that with particles because you can't pull with particles, you can't attract. Then if they can't do, and you can't explain two magnets, one attracting another with particles. So if you cannot explain absolutely any of the invisible phenomena of Mother Nature's with particles, wasn't this a time to apply Karl Popper and say, hey, you know, just one instance falsifies your theory. Here we have 10 of them. They all falsify your theory. So at that point, you had to reject the particle. You cannot explain anything with particles. Period. We're done. And they didn't apply Karl Popper there. They give lip service to Karl Popper. I don't know why, but then on the other hand, they never apply it to the particle hypothesis. Okay? And yeah, they should have erased the board and start all over again. They should have brainstormed new hypotheses, new mediators, okay? Which is what we did here. Okay, we have a new proposal on the table. Okay, here's another problem to keep in mind. Actually, like 4 of them I have here. The 2 of them went by. Here's the third one. Third one is that theory is not a description. A theory is an explanation. Okay, I hope that's clear. Someone says, what's your theory? You're going to explain something. Oh, I think Johnny broke the window with his baseball bat. That's, I think, how the glass ended up on the floor. You're explaining something. Or how did this woman die? Well, she was stabbed to death. You're explaining something, how something happened. That's a theory. And it's not a description. If I describe a chair and say, yeah, it has 4 legs, 1 backrest, 1 seat, did I do science? Is that what science is? Just a description? If I measure and say, oh, this table measures 1 meter, is that a theory? Is that science? This is the issue. And quantum theorists admit, concede, and confess that all they have are descriptions of the invisible, microscopic, atomic, and subatomic world. That's all they have, descriptions, mathematical descriptions. That's all math can do, describe. Math cannot explain causes, mechanisms. Therefore, they don't have a theory. There is no so-called quantum theory. The quantum theory, like Khalili just said a minute ago, is all irrational, illogical. So if it's irrational and illogical, you might as well put angels, spirits, God, black magic, whatever you want in there. Because he says it's going to be irrational. He doesn't have a rational explanation to give you, therefore he has no theory. You know, he just says, yeah, bring your magic wand, this is how we do it in quantum mechanics. Yeah, no kidding. So you don't have an explanation. Okay? So if you don't have an explanation, you don't have a theory. There is no such thing as quantum theory. There's quantum description, and a description is not a theory. Keep that in the back of your mind. Okay, so that's what it is. All they have is a description, and mathematical physicists refer to these descriptions as theories. They say, oh, quantum theory, it's been proven, it's been confirmed, it's very accurate. Huh? What are you talking about? They're talking about measurement. They're talking about equations. They're not talking about theories. There is no such thing as a mathematical theory because mathematics cannot provide explanations. It's mathematical descriptions. That's all that mathematical physics does, the math part. The physics part is all irrational physical interpretations, which they dismiss afterwards and say, oh, that's philosophy anyways. Philosophy of science, philosophy of physics. They give service to irrational physical interpretation, dismiss them as philosophy. Okay? Okay, and last but not least, but this is a serious problem also, I want you to keep this one also in mind. This one here. if I can get it. It's the issue that the general public is completely unaware of all this. The general public is hypnotized, blindsided, totally unaware that mathematical physicists have no understanding whatsoever how the universe works. And by that I mean an explanation of the invisible, intangible agents and mechanisms. That's what I mean when I say explanation, theory. We're talking about mechanisms. What is the mechanism that Mother Nature uses out there to do gravity, to do atom, you know, the quantum jump, to do light, to do magnetism, to do electricity? This is what we want to understand. The physical interpretation, the causes, the mechanisms. That's what I'm talking about, okay? The layman has been conditioned to accept everything on the basis of authority, that mathematical physicists can do no wrong, that technology is proof of theories, you know, such as quantum mechanics and general relativity. The typical defenses are, you'll hear this all the time, we wouldn't have computers if QM were wrong. In fact, Al-Khalili says that same stupid thing. So it means he never learned anything in the monastery where he studied, okay? Or we wouldn't have GPS if GR were wrong. Are we talking about GR description, or are we talking about the explanation? Are we talking about warp time? Is that what we're talking about? Or are we talking about Einstein's field equation? What are we talking about? Okay, so keep all this in mind, because this is where the problem is, especially with the slit experiment. And these rejoinders are irrational. They show a gross misunderstanding of the issues at hand and total misconception of the scientific method. These people have no idea what science is. Anyone who uses these types of arguments, okay? Okay, and here's an example of that. Here we have a crane lifting magnetically a bunch of iron, a bunch of metal, okay? Does that guy know exactly how a magnetic field works, how it attracts? No, he doesn't have to. All he needs to do is be able to use what he's already proven through experiment in the lab. In other words, someone goes to the lab, uses a magnet to pick up things, they make it stronger, okay? And once it's strong, they say, well, I need a stronger one for this. They get you a stronger one, they manufacture it, they learn how to manufacture it. No one in the entire line knows what a magnetic field is or how it does its magic from afar. Why? Because they can't see it or touch it. And so they don't even have speculations as far as magnets. So this is the same thing with quantum mechanics. Quantum mechanics, you know, we didn't develop the computer because of quantum mechanics. You know, I mean, I worked in the industry for many years, and we developed the chip by trial and error. You know, in fact, they're improving the chips every day. Do you think those guys go in there and say, oh, we have so many positive carriers here and so many negative carriers there? In general, what they do, they do have an understanding of that stuff. No doubt about that. But what they do, they test things out every day, and they say, well, we put too much boron here, we put too much phosphorus over here, or whatever. You know, and so they play around until they get it right. That's it. Did Edison know anything about electricity? No. In fact, we give him too much credit. Thomas Edison was a businessman. That's all he was. He wasn't anything beyond that. All he did was have his people, maybe he himself participated, developed the filament until they got it right. They got a long-lasting filament, and they sold it. And they did all kinds of contracts with companies, with Morgan, etc., and they built General Electric, and they moved forward. Was he a scientist? Absolutely not. He had no idea what electricity is. Okay, he died not knowing what electricity is. So, yeah, it's trial and error. And so to think that an experiment proves your theory, or to think that technology, the fact that we develop technology, proves the theory, the physical interpretation, the explanation, the mechanism. No, absolutely not. One thing has nothing to do with the other. Now I always mention, you know, the nuclear bomb, you know, the atomic bomb. People say, oh, all these quantum guys, you know, they developed the atom bomb. All that math, you know. Well, the Iranians today know all the math that the West knows. They don't have a bomb. Okay, so I hope that sinks in. Okay, so how does Al-Khalili start his presentation? Well, he quotes Richard Feynman. And he only gives one quote from Richard Feynman. I'm going to quote a couple more because I want to drive home the point that these guys have no understanding whatsoever of the causes, the mechanisms. And you're going to hear from the horse's mouth here. It's going to be Richard Feynman talking from his grave right here. Okay, so these are from his lectures. Okay, and so here's what Feynman says in one of his lectures, Volume 1, Chapter 37. You can look it up. Quantum mechanics is the description, not an explanation, description of the behavior of matter in all its details, and in particular of the happenings on an atomic scale. Okay, things on a very small scale behave, talking about behave, okay, not causes, behave like nothing that you have any direct experience about. Yes, yeah, we do have experience. The problem is that you never thought, dear Richard, what could be mediating all this stuff. You were thinking of particles, and you cannot explain anything with particles, and therefore, if you keep insisting on particles after 10,000 years, well, you got a mental problem. That's the issue, okay? They do not behave like waves. They do not behave like particles. Exactly. They do not behave like clouds or billiard boards or weights on springs or like anything that you ever seen mediated by particles. That's the part that was missing in Feynman's talk, in his presentation. Okay, so Feynman moves on and he makes this other statement. All these statements come from him, and it just shows you that they have no clue whatsoever. I hope I'm still on. I've had some problems here and there. I think I am. Okay, let me know if there's a problem. Okay. Again, YouTube had some kind of problem. I was going to complain, and somebody else beat me to it. Apparently, they say they're working on that type of problem. Some error that we're all getting. Okay, it says, this is from Feynman again. Newton thought that light was made up of particles. Particles, particles, particles. Particle man, particle man. But then it was discovered, as we have seen here. Okay, thank you, Tesla. But then it was discovered, as we've seen here, that it behaves like a wave. Okay, so it does or doesn't behave like a wave. It does or does not behave like a particle. Well, we keep going back and forth, right? Later, however, in the beginning of the 20th century, it was found that light did indeed sometimes behave like a particle. Okay, historically, the electron, for example, was thought to behave like a particle, and then it was found that in many respects, it behaved like a wave. Okay, so it really behaves like neither. Now we have given up. They've thrown in the towel. Okay, they have no idea how light behaves or how the electron behaves. Okay, these are things that quantum supposedly is an expert at, right? We say it is like neither. So we don't know if it's like both or like neither. Okay, so I want you to keep track of all this. This is Feynman. He was a Nobel Prize 1965, I think. Okay, and a couple more. In this chapter, we shall tackle immediately the basic element of the mysterious behavior in its most strange form. Okay, we choose to examine. Listen to this is the one that Jim Al-Khalili quoted. Okay, we choose to examine a phenomenon which is impossible. Absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. And again, he cannot explain it with particles. That's the issue. You cannot explain it with quantum, okay, packets or whatever. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. In other words, they can't explain how it works, okay? We will just tell you how it works. He's going to describe. He's going to describe what they did in the lab and what they couldn't see. So he's going to infer what he couldn't see, and always the inference turns out to be particles. Now maybe at this point they should have said, hey, we got to quit the particle. Do you think it even crossed their minds for a second that they could think of something else, that it wasn't wave or particle? This is the issue, okay? I'm telling you how it works. We will have in telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics. Okay, and here we have one more. Here he says the complete theory of quantum, again, theory. That's not a theory. If he's just going to describe it, it's not a theory. Theory is give me an explanation of a mechanism of quantum mechanics which we now use to describe atoms. A theory to describe. You see how they use these words. They don't know the difference between a description and an explanation. And in fact, all matter depends on the correctness of the uncertainty principle. Since quantum mechanics, listen to this, since quantum mechanics is such a successful theory, yeah, it's always successful. When you have the wolves guarding the sheep, it's always going to be successful. And all these people, you know, they block everyone who questions the physical interpretation. They don't even allow those things printed in their magazines, which are, you know, the respectable journals, right? Since quantum mechanics is such a successful theory, our belief in the uncertainty principle is reinforced, okay? But if a way to beat the uncertainty principle were ever discovered, quantum mechanics would give inconsistent results and would have to be discarded as a valid theory of nature. Oh, so all he wants is for me to destroy the idiotic, the irrational uncertainty principle? Hey, it's a piece of cake. Here, let me explain it to you. Here's a ball, right? I have no place to put it. When the ball is moving, it doesn't stand still. And when the ball stands still, it doesn't move. So the more you know about its position, the less you know about its momentum. And the more you know about its momentum, the less you know about its position. Now, how intelligent was Werner Heisenberg, okay? And of course, his buddy Bohr, you know, said, hey, you come up with that nonsense and I'll give you a Nobel Prize. And they just kept giving Nobel Prizes to each other. And yeah, so Werner Heisenberg, he said, yeah, when the ball moves, it doesn't stand still. And when it stands still, it doesn't move. And he can't get them to do both at the same time. Oh, my God. This world, Mother Nature is so cruel. Okay, yeah, Heisenberg's uncertainty principle is absolute nonsense, and he says it's the foundation of quantum mechanics. Okay, last one here, also from Feynman. He says, one might like to ask, how does it work? What is the machinery behind the law? Yeah, that's what mechanisms. That's what we want to know. No one has found any machinery behind the law. No one can explain any more than we have just explained, quotations. No one will give you any deeper representation of the situation. We have no idea about a more basic mechanism from which these results can be deduced. That's the status. 60 years later, Al-Khalili says exactly the same thing. He says, we have no idea, we don't know. But they've proven it. Quantum has been certified as the most accurate, most successful theory, but they don't know. Now you tell me how much sense that makes. We have a problem. We got to find out what the problem is. How can on the one hand they tell the public, you know, we don't understand all this stuff, and then on the other say, oh, we've proven it, it's more accurate than anything else we've had, it's been, we've confirmed it. We got a big problem. We got a problem because these people are giving us the runaround with their double talk. We need to find out where the problem is. Okay, so let's move on here. What is the slit experiment? Let's give you an idea. So what Al-Khalili is going to try to explain is the slit experiment, the one that drives the quantum mechanics all nuts. Okay, and here it is. Just very simple. You shine a light through two slits. What do you expect to see on the screen? Well, you would think that if you shine a light, okay, you would see maybe two little shadows there. Okay, this is what one would expect. You shine them through two little screens, like two windows, and you should see maybe a shadow of the windows, right? Something like that, okay? And instead what they see, okay, is this. They see fringes. They see many shadows or many lights or whatever. It's like if light broke apart and just went in different directions. Okay, so this is the problem. Okay, and so what do the mechanics have in mind? People like Al-Khalili. Okay, well, what they have in mind is what this guy illustrates. He's from one of the universities, And what they have in mind is what Einstein and Bohr discussed in 1927 at the fifth Solvay Conference. Okay, and it goes like this. Essentially, the source shoots a particle that hits or strikes the slit, the partition. Okay, and so it hits it and bounces inwards. And then the other one bounces off the other slit and bounces outwards or inwards. In other words, they're all bouncing in against and going into the screen. That's how these people see it with photons. They also see it like this with electrons. Okay. What is the problem with this? And again, I should mention one more time that Einstein and Bohr discussed this same thing, and they said, well, if the photon hits the partition, hits the little window seal and pushes the partition over, well, then we have a problem with the uncertainty principle, because now you can't tell where the partition is, because now it's moved, because you have this photon hitting it. Okay, so they discussed this hours between Bohr and Einstein in 1927. Today, even to today, everybody's discussing these things, and they never reach a solution to all these question, because again, they're doing it with particles or with waves. That's the problem. Okay, so here is a little trick that I play on them. I'm going to remove the slits. Okay, I'm going to leave only the center. I'm going to put a needle instead of slits. Okay, now what is it? What is the photon bouncing against to come inwards? Okay, you see what the problem is? This would create a serious problem for quantum, because quantum is saying, hey, it bounces and comes inwards. That's the way they see it. And it turns out that now I remove the slits, and all I left is a needle. You can also do this with a human hair. In fact, just to make sure that you understand, I'm not claiming responsibility for that. I'm saying that good old Newton, he puts it in his book of optics, and he says he used his hair and saw shadows. And the reason I found out about this as well is that Thomas Young, in his second experiment, used Newton's hair experiment. Okay, he did it the same way. He said, look, he measured, the fringes with by putting a human hair. So you do not need the slit. Okay, you can do it with hair or with a needle. In fact, here it is. I did this experiment a few years ago, and you go all the way to the end and you'll see the fringes, okay, on the wall. That's what it looks like. You can do it in the comfort of your house. Just get a laser pointer. It's got to be monochromatic light. And you do what I did here. I'm going to show it in a second here. You're going to see that there's going to be a needle mounted on a chair. Very expensive, very dangerous experiment. Always do it in the presence of a trained relativist. Okay, and there you see this the fringes on the wall. Okay, so don't take my word for it. Just buy yourself a laser pointer. Get yourself a needle. Okay, and you'll be able to do this experiment. Okay, and here it is. I'll change my hands. I'm right-handed. Okay, here's a needle just stuck to a cork. Okay, and I'm just going to put white light. Okay, just shine it on there. Here, the other one is the red one, but you don't see that one. Okay. Anyways, just point it. Have them fixed. Do it against the wall. You'll see the fringes. You don't need slits. You don't need to do it the way they do it in college. Those advanced people, those mommy's boys. No, you can do it at home. You can do it at home. Just point laser pointer to a needle and you'll see fringes on the wall. Do you need to know distance? Do you need to know the speed of light? Do you need to know any math? No, you need to explain why you see the damn fringes on the wall. That's a physical phenomenon. You don't need any math. You don't need any distance. You don't need to measure anything. You don't need to use the little d's and the little a's and the little x's. None of that. You don't need any equations. Just point it, get the fringes. Once you see the fringes, say, how does Mother Nature do this trick? It's a qualitative answer. Okay? Very simple. You just got to explain it. Okay? Okay? And where was the problem? Well, one of the big problems is that the mathematicians never discovered that there's a third kind of wave. Okay, all of them go to college, they get their PhDs, they only learned about two waves. They learned about these two waves, okay, the longitudinal and transverse wave. They never learned there's something called a torsion wave. Okay, in fact, they dismissed torsions, I don't know for what reason, okay, because that's what light is. Light is not a longitudinal wave like sound is. It's not a transverse wave for sure. It doesn't go up and down. And by the way, what you're staring at as far as the transverse wave is concerned, what you're staring at is a bunch of vectors. Those arrows, those are not engine arrows. Those are vectors, okay? And what you have is a ridiculous mathematical contraption. You can call it a mathematical object where you have vectors moving, you know, from A to B. What sense does that make? Okay? Torsion, well, for that you need a rope. Okay? You can produce it with a rope, for example. Okay? You can do it with a chain. Any elongated object, you can do it. Okay? That's what we're going to propose. Okay? And so here's the difference between quantum and the rope hypothesis, which is what we propose here. Mathematical physics, you have all discrete particles. The rope hypothesis, all atoms in the universe are interconnected. By what? By what we call the electromagnetic rope. All atoms are physically connected. Okay, so that's the proposal. Okay, and with that, we're going to explain the slit experiment very easily. Okay, and so first, let's get an idea of what light is. Is light a bunch of particles? Is it a bunch of waves, or is it torsion between two atoms that are united or bound to each other by the electromagnetic rope? So you have the quantum jump there. Atom is pumping back and forth. That's the quantum jump that good old Mr. Bohr discovered. Even though he got the wrong interpretation, he said it's the little electron bead that jumps back and forth for no reason whatsoever. How that electron bead was tied to the nucleus, he never explained. Even to this day, they have no explanation for that. Here, it's very simple. You know, the threads make up the atoms themselves. And those who've seen the previous videos know what I'm talking about. I'm not going to go over that again. All I'm saying here, we have comparison of the different mechanisms proposed. Quantum mechanics proposes the two upper ones. Rope model proposes the bottom one. We have atoms pumping back and forth, little hearts that are pumping torsion waves through the electromagnetic rope to other atoms in the universe. That's the model we're going to use. Okay. Okay, and so how do we explain the slit experiment with this thing, with this rope, with these atoms, interconnected atoms? Okay, here we have the lights out, okay, and we have the ropes are already connected. Remember, all atoms are interconnected, okay, so the ropes are already there, are in place, okay. All we do when we turn on the laser light, okay, is we stimulate those existing ropes, okay. The atoms that are connecting the source to the slit, for example, in this case, and from the slit to the screen. And what you have is all those ropes are now torquing faster, okay? Because the atoms are pumping faster. That's what the increase in frequency does. It shortens the lengths of the rope. So the lengths of the rope are now shorter. That's why it comes within the visible range, okay? And here's another vision of this, sideways, I guess. This is where the light's turned off, okay? What happens when we turn the lights on? We're just going to go in two steps here. First, we're going to look at what happens to the ropes that are connected from the source to the slit, okay? You can see they're turned on, okay? Why? Because they're at a higher frequency, okay? And now let's look at the full picture, and that's now the, well, let me get that up there. Okay, so now you see the fringes. Why? Because you have these ropes that are suddenly torquing at a higher frequency. In other words, shorter lengths of the ropes, and they're going to interfere with each other. Okay, what do I mean by interference? Well, now it's standard wave interference, both constructive and destructive. Here you have a picture of that. Okay, let me get back in here. Okay, and what you see is, you know, when the ropes are in phase, then you have constructive interference. When the ropes are out of phase, the links, you know, are out of phase, the then you have destructive interference. And then at the bottom you see that there's you can have different angles. That's why you have a nuanced fringes. I mean, if you could really see all those little that, you would see that there are fringe. The fringes don't go directly all the way to black, to darkness. No, there's fringes all the way from one fringe to another, but all those fringes are different tones or different strengths, okay? And that's explained by the fact that you have different angles of the rope, okay? So we do have an explanation for that. And again, it's all, those who studied wave mechanics, this is nothing new to them, okay? It's just wave mechanics applied to a rope, to a real physical object, not like in mathematics where they use waves, which are vectors, and particles, which are zero-dimensional and go backwards in time and come out of the void and all that nonsense. Okay. Now this is all rational. Okay. Rational. Why? Because you can make a picture of it. You can illustrate it. Okay. And because you can simulate it. And this is, again, a different picture. You can see constructive and destructive interference, more or less how they look. This is the way they end up on the screen. If the two ropes one coming from one slit and the other one from the other, or from the two sides of opposite sides of the needle, right? When they meet, if they're in sync or in phase, then you have constructive interference. And if they're out of phase, you have destructive. Very simple. Let me give you a dynamic version of this. Okay, this is the dynamic version. Let's hope you understand it. It's not. You got to get used to this. Okay, the top one, the lights are turned off. What do you see there? Well, if you compare the top one with the middle one, the before turning light and the bright band, you'll see that the rope, it has shorter links in the middle. The one in the bright band has shorter links. That's what the difference is between those two, okay? So the first one, it's below the frequency that we can see, okay? So it's just, or it's a shadow, essentially. And now you turn on the light, what happens? Suddenly you turn on the light and the frequency goes up, and now the atoms are pumping faster and wider, either or both. I still haven't figured that one out completely, okay? But that's for theorists also to put their heads here. And it's either the atom is pumping to a larger balloon. Those are the famous orbitals of quantum mechanics. They're actually balloons, okay? And these balloons are pumping back and forth, okay? They're quantum jumping there. And if they pump very high, obviously they're going to torque the rope to a higher frequency, and because of that, it stimulates the atom at the other end, both at the slit and at the screen. Okay, and then the one at the bottom shows you destructive interference. The difference between the middle one and the one at the bottom, if you look at the ropes on the left-hand side, the two ropes in the middle, they are in sync, they're in phase. The two ropes on the bottom left, they're out of sync. That's what I'm illustrating there, okay? And that's essentially the mechanism proposed for the slit experiment. So we do have a rational explanation, okay? It's this is just an introduction, okay? People have a million questions after this always, and I've discussed those in our conferences. We had the one in Buenos Aires, what was it, 2017, and I discussed the slit experiment there with the folks. Obviously, my presentation was on the basics, and then if you have 1,000 questions, as people usually do, well, then that's when we get some beers and we discuss the finer details, okay? So this is just an introduction so that you get the idea, the mechanism. What are we proposing? Okay, you can see that whereas quantum mechanics says, oh, it's beyond imagination, nothing we can imagine can explain it. Well, here we have something that is imaginable. Okay, you have essentially, here we have my little rope, one of the ropes. I got a bigger one, a little smaller one. Okay, if the see if I get this right. If one is let's see this one. If one is up and down, the other one is sideways. Okay, right. One is north-south, the other one is east-west. That's destructive interference. If they're both, if they're both north-south, for example, then you have constructive interference. We're done. That's how simple it was all these years. Just in case, entanglement, oh, that's a hard one. That's a really tough one. It's for babies. Here's entanglement. Entanglement means that if something is clockwise over here, it's counterclockwise at the other end. And if you switch this one to counterclockwise, the other one is now clockwise. Okay, here it is, very simple. Okay, from my end, I'm going to twirl it clockwise. Hopefully in your end, it's going counterclockwise. Okay, Mother Nature understands counterclockwise and clockwise. She doesn't understand positive, negative, north, south, all that garbage from math. She doesn't understand that. She understands physics. Physics is clockwise, counterclockwise. Okay, so now I'm going to turn this mine counterclockwise. Hopefully yours is twirling clockwise. Okay? Simple. So difficult, so many years, unimaginable. And yeah, if the rope extends from the Andromeda galaxy 2.2 million light years away, okay, to the Earth, well, that rope can go this way or it can go that way. And people say, well, how about when we immediately turn in this one counterclockwise? It's going clockwise. Okay, fine. Now we'll turn it counterclockwise. Does that rope all the way to the Andromeda galaxy completely turn in the opposite direction? There's several answers to that. I'll just give you one to ponder, okay? This is important for you to think in these terms. The mechanics, the quantum mechanics, they have no idea what they're doing in the lab. Okay, we saw Mr. Tonomura there saying that he handled one electron at a time, and we showed him that that he wasn't handling one electron at a time the other day. And if he thinks that he handled one electron at a time, and that's what he published, and that's what the mathematicians think, when obviously if an electron is a balloon that encapsulates the proton star, then he can't handle that one at a time like a little bead that's rolling around the atom. Those are two different notions. See, these people are saying, oh, I handled one electron at a time because he's got some kind of electricity moving there, and his idea of electricity is a little bead that moves from atom to atom. But if that ain't what he's seeing, in other words, that's not the real world, then he's not handling one electron at a time. And if he can't handle one electron at a time, much less can he handle a photon at a time, which is what all these people claim. I think Aspect, when he ran his experiment, I don't know if he got a Nobel Prize for that, but a French guy, he did the EPR experiment, okay? And he said, he proved it. He proved that what Einstein said was impossible. EPR, Einstein, Pulaski, Rosen, they said it's impossible. These guys were able to do the experiment, okay? But if he thinks that he handled one electron or one photon at a time, well, he's crazy. Because there is no such thing as a photon. Photon is just a link of the rope. That's what it is. That's what they've been thinking. It's a particle all these years, okay? And so, they think that a particle is moving. And so they say, well, is the particle moving at the speed of thought from the Earth to Andromeda? Well, we need to figure out under the rope model what these people are doing. We need to find out if they're actually torquing the same rope. Okay, they could be torquing a parallel rope for all we know, because right now they don't even know what they have. They can't see in that world, so they have no explanation. They think they're moving one photon at a time. They think they're moving one electron at a time. If photons and electrons are not particles, we have to redo the whole thing. We got to erase the board completely and start all over again and fire all mathematical physicists from science. We got to get rid of them, all of them. So anyone who's got a degree in mathematical physics has to get out. For sure he has a deranged mind. Okay, so we don't know what they're doing. That's the first answer. There's more answers than that. Okay, so where does this take us? Here. If this is correct, if this is what Mother Nature's doing, she's doing it with the electromagnetic rope, all atoms are interconnected, physically interconnected, well, then we have a solution also to Arthur Eddington's warpage of space. It's not done by light curving around the so-called gravity well of the sun, no such nonsense. No, it's that the star at the far end that we are able to see behind the sun during an eclipse, it's photons. In other words, there's no photon traveling. It's rope connected from one atom to the corona of the sun is being relayed. That same frequency is being relayed to your eyes or to whatever source, target you have there. That's it. So it's done with straight lines. Light never travels in curves. The way light curves is by having a bunch of straight ropes forming what appears to be a curve. Okay, that's why we can see around corners. We have all this refraction and reflection going on. What is it? Just signals going along taut ropes. Rope is always straight as an arrow, or even straighter, I guess. Okay, and yeah, so this would give you an idea that that both these experiments, if I can get this up here, okay, both these experiments are the same. Let me get it back up here. Where did I put this now? Here it goes. Both these experiments are the same. In other words, the slit experiment on the right and the gravity well, the warping of light, the bending of light as they call it, are the same experiment. Okay, they're both essentially the same thing. What you have is relaying through electromagnetic ropes. Okay, so let's give you the summary. And I don't know if to call them alkali or alcohol maybe, I don't know. Here it is, Mr. Alcohol. Okay, and so what are the conclusions or a summary for Mr. Al-Khalili? Well, Al-Khalili and his buddies, the mechanics, have no idea how Mother Nature does the slit experiment. Okay, I think Feynman, even Al-Khalili, 60 years later, he's saying exactly the same thing. Okay, in vain and against all odds, Al-Khalili and Alkali and his buddies continue to explain the slit experiment with particles. That's where the problem is. The mechanics do not understand the difference between an explanation and a description. Not a single mathematical physicist on planet Earth understands the difference between a description and an explanation. They use these words, sometimes they use them in different contexts, but later on they talk about explanations when they have absolutely no explanation in all of mathematical physics for what? For the invisible mechanisms of Mother Nature. Not one. Why? Because they do them all with particles. And light is mediated by neither waves nor particles, but by a pair of twined threads, a DNA-like rope. And unlike slow, one-way, zigzagging, longitudinal and transverse waves, a torsion propagating along a taut rope spins in situ, bidirectionally, rectilinearly, and very fast. The rope explains the slit experiment with flying colors. We have no problem with the slit experiment or with entanglement. Okay. So what are the questions people typically ask? I'll ask them because I already know what people ask. Okay, I've had 20 years of this, people just asking the same questions. And the main one, I'm just going to deal with the main one here. Main one is, how come we can't see or touch these ropes, these electromagnetic ropes? Let's go to the lab. Show me, prove to me, demonstrate their existence. Okay, so let's answer these these individuals. Okay, what is the answer to all that? Okay, so let's go over that. These are the answers. Okay, we start with the first one, and the way we do it is we read to them by the book, the Miranda rights. That's what we're gonna read to them. The golden principle of physics, which they never learned. Not a single mathematical physicist, so-called physicist, ever learned in his life. Okay, he never learned it. He never learned it in high school. He didn't learn it in college. He didn't learn it when he graduated. He didn't learn it when he did, experiments or whatever, or in his work, professional work. Physics requires an object. You can't do physics without an object. Okay, I don't know how much to enforce that, to rub that in, for people to memorize it. Okay, you can't do physics without an object. If we wipe out all matter from the universe, there is nothing there, not a single, not space made of particles, but space made of space. Nothing, absolute nothing. What is nothing? That which has no shape. Right? That's nothing. That's the definition of the word nothing. That's the definition of space, which is a synonym of nothing. If you have absolutely nothing, there is nothing going on. Nothing is happening. There is no phenomenon. So whenever there's a phenomenon, there had better be an object. You better have an object. What is an object? That which has shape. Okay? An object is not what the mathematicians have used all these years. Okay? Here it is, the rundown, because this is what people raise as answers to that question, what is an object? Well, this is what an object is not, okay? And until you get this underneath your belt, you don't know the first thing about physics, okay? An object is not that which we can see, that we can touch, that has mass, that has volume, that moves or can move, is made of parts, is visualized through time, that we can use in a sentence, that has color, that exists, is 3D, is not standalone. And I don't know how many more. These are the ones that I've collected over the years, because people come up with all this nonsense. This is what they think an object is. Where do they get this? From ordinary speech. They go to the dictionary and say, well, this is what it says here in the dictionary. It says an object is that which I can see and touch. That's the typical definition. And that's the one used by mathematical physicists. And that's why they say, let's go to the lab. Let's see if we can see or touch the rope. That's what they want. They want to see or touch. They want proof. They want evidence. Which means that they have not the slightest idea of what the scientific method is about, okay, or physics. Physics is an explanation of a mechanism. Mother Nature deliberately, God, Father Universe, one of those guys, maybe the devil, one of those guys with his superpowers made light, gravity, magnetism, invisible and intangible, unhearable, untastable, unsmellable. You can't go to the lab, run an experiment, to see, touch? What are you going to find out? You want to know gravity? Hey, very simple. Here's gravity. Okay, you let go of the ball, and it falls to the floor. That's the only experiment you ever needed. Now you got to explain it. No more experiments. We're done with experiments. Now we need to figure out how gravity is done, how light is done, how magnetism is done, how electricity is done, how the atom does its quantum jump. We have to figure it, what it looks like also. We got to figure out these things, and you're not going to figure them out by running an experiment. You're going to figure them out by getting a beer, closing your eyes, moving your head back, and visualizing. You have to imagine how Mother Nature might be doing that with objects, because she better be using some kind of object. What is an object? That which you can touch or see? No, it's that which has shape. And the rope obviously has shape, okay? In fact, here it is. I'll show it to you. That's the difference between the ridiculous thing that James Maxwell proposed, a bunch of vectors moving through space, okay? And of course they didn't know what it is, so some people say it's the undulation of nothing, others say it's the undulation of who knows what, of particles. They don't know, they have no idea. But the rope, you know what a rope is. It's got two threads, twined threads, we're done. So what they've been staring at all these years, what they thought they've been staring at, they thought it was a wave, a two-dimensional flat wave, no, it's a three-dimensional rope. That's what they've been staring at. And the rope interconnects any two atoms. When the atoms pump, the rope torques. We're done. That's how simple it was. We live in a very, very simple universe. Two atoms bound by a rope. That's the model. That's the simplest model you can think of. Simple and symmetric, by the way, okay? Okay, so yeah, the issue there is the definition of the word object. The word object is not that which we can see or touch. It's that which has shape, okay? Okay, there it is. An object is not see, touch, mass, volume. An object is none of those on the left-hand side. An object is that which has shape. It's got to be a standalone object. It should be the only object in the universe when you present it in physics. You point to it and say, table. That's the only table in the universe at that moment in time, when you name it. Only then can the ET, the visitor from outer space, the Klingon, understand your language and say, oh, okay, table refers to that object there that he pointed to. Now you can use it for anything you want in your theory because you've identified the object. And that's the way it works. And obviously quantum mechanics cannot do that. What are they going to point to for a wave? What are they going to point to for a wave packet? Corkscrew? So this is the issue. The issue is these people have no objects. They have only mathematical objects. Okay, with that, I'm going to move on to some of the questions, see if I can address them real quickly here. First question, what is this? Fellow asks, how does Founder's effects explain the origin of this inbreeding you spoke of in your Is your idea that Adam and Eve is what caused it? Exactly at what point two people started inbreeding? Oh my God. Okay, so let's answer. Here's the answer to this. It's got to do with the extinction theory. We're the last humans on Earth. So it's not going to go beyond this. Okay, here it is. Let's put it next to it so we can compare notes here. Okay. And the first one is, Founder's effect doesn't explain or have anything to do with inbreeding. I don't know where he got that. Okay. Adam and Eve is Bible stuff, so you're probably in the wrong site. You should perhaps look for a YouTube site that deals with Christianity or Islam or something like that, okay? Okay, yeah, see you, Tesla. Then when humans started inbreeding is irrelevant in physics and for extinction. So the question is irrelevant. And when is a mathematical issue? Strictly, it doesn't matter. I mean, I don't know what the context is. I don't know why when is important. The date, not important at all. Okay, when we started inbreeding, I don't know. That's yes. I wasn't there. I came many centuries later, so I don't know when. But you can talk to one of these geneticists. They typically do all these calculations of when when things started to occur, when they started to happen. Okay, they can probably inform you better. Can you make a recommendation on info on Gravity Probe A? Gravity Probe B info is out there. There is a guy who flat stated the purpose of Gravity Probe B was to confirm GR. More or less, I tend to agree with that. Okay, here's my take on that. Okay, here's Gravity Probe A first. Let's go with that one first. Gravity Probe A was launched to check different times at different gravities, essentially. Gravity Probe A carried an atomic clock to verify and confirm the structure of space and time. The mission was designed to measure time as it rose through weaker levels of gravity, and the experiment confirmed, as it always does, that time ran at different rates as the strength of gravity changed. Okay, so that was the Gravity Probe A, which they used essentially to understand where they were going to put the GPS satellites, at what levels. They needed to have a pragmatic idea, experimental evidence of where they were going to put the satellites. That was one issue. And then here we have Gravity Probe B, okay, and let's see if I can get myself in here and put this over here. And Gravity Probe B was launched to confirm Einstein's general relativity, and wouldn't you know it, they did confirm it, or else they would have all been in trouble. Gravity Probe B was designed to confirm, never to debunk or refute, right? God help relativists otherwise, right? That space is a physical object. That's what they wanted to prove, that space is a physical entity, okay? And so the NASA relativists wanted to show the world that the Earth drags invisible, intangible space around itself like a tornado swirls air and dust around itself. That's they wanted to show that space is some kind of tornado, or that Earth, when it spins, is this tornado that drags space around itself. So yeah, in a way, gravity probe B was designed to confirm, to prove, as they call it in mathematical physics, that Einstein was correct. Because if he was incorrect, then there would be a lot of problems. And these are the conclusions these people reach. They reach the conclusion that space is a physical object and that therefore it can be warped and molded and so on by gravity. So that's what we have today. So when you say, well, what prevents the Earth from flying out of the solar system? They say, well, it's warp time. Space, time, time is warped. I thought time was a concept. How do you warp a concept? How do you warp love, But that's the explanation they give you. Okay, another comment. Okay, here we go. And this fellow says, if fire plasma is just a concept, is everything not only a concept? Since we all were a sun once, okay, big fire, and the supposed Big Bang was just a big fire too, that changes its form. The atoms which compose our Earth were certainly only fire once, okay? So no fire and plasma are not concepts. Otherwise, everything is just a concept. Is being solid just being a colder fire? Fire cannot be simply moving, then it would be called movement. Okay, what is the problem with what this gentleman brings up? Here it is, in a nutshell. My God. I'll put it over here. Okay, this is the problem. What does the word concept mean to you? I mean, he never defined the word concept. We don't know what he's talking about every time he pronounces the word concept, or object for that matter. Why didn't you start by defining the term? I mean, he could have said, look, this is what I think a concept is, or this is my definition of the word concept. Otherwise, we don't know if plasma is a concept because you haven't defined what a concept is. Okay, I did define it, okay, and here it is. It is impossible to reply because we have no idea what you're referring to when you say concept, and yes, confirmed, plasma is a concept according to the scientific definition of concept. Okay, concept, a word that embodies or makes reference to two objects or two words treated as objects momentarily. Okay, it's a relation. That's what a concept is. Okay, and so that's what plasma is. Why? Because anything in motion, and plasma is ionized gas. Ionized meaning something is happening. Okay, you need two frames in the universal movie to produce plasma. You can't do it in one frame because you have to ionize the atom. You have to pull an electron if you're going to use the quantum version, right? So something is happening to that gas. So plasma is not gas. Plasma is ionized gas. That means plasma requires two frames in the movie. You have a relation now, and all relations are concepts. In other words, relation is a synonym of the word concept. So yeah, under the scientific definition of the word concept, plasma is a concept. You don't like the definition, you have only a single recourse, and that is to define the word concept, which no one has in the last 10,000 years either. Okay, so that's another problem that we have from mathematical physics. People whose religion suddenly throw a tantrum and dismiss definitions as semantics. Yeah, that's why we don't see any definition there from his side, the blue side. And they fail to realize how important definitions are in science. And so do mathematical physics. They never define any word. They don't know what a point is. They don't know what a line is. They say these terms are undefined. They don't know what mass is. They don't know what energy is. They don't know what a field is. They don't know what anything is. But they have confirmed and proven every one of their theories. Yeah, sure. But they haven't defined any term. They don't know what an object is above all. I mean, that's the first word they had to define. Nobody ever defined it. That's my biggest contribution to science, the definition of the word object, by the way. I feel proud of that. Okay, another question. What would it take to break the rope? Would a resonant frequency be able to sever the ropes and free the bound particles? No, I don't think so. What's the underlying hypothesis? And that we'll put it in the right context, if I can get this thing up here. Here it is. Here's the right context, okay? What's out there? A single closed-loop thread. That's all that's out there. We can say that's all that exists, okay? And that's a very fancy word, exist. That's the only object, okay? This thread turns into everything, every atom in the universe. So the thread has certain properties, and the thread is, listen carefully, made of a single piece, therefore it cannot be broken, okay? It is malleable despite being made of a single piece. Okay, that's a long story. A lot of people have questions on that, millions of questions, in fact. But yeah, it's malleable, made of a single piece. You can't cut it. You can't touch it. It doesn't have the property of touch. Okay. It takes a long time to understand when it becomes touchable, only under certain circumstances, certain architectures. And that's a long story. I'm not going to deal with that right now. But for all practical purposes, the thread cannot be touched, cannot be seen, okay, because you don't have light there, okay? And it makes up all the matter in the universe. That's essentially it. And because of that, no, the rope which is made of this thread cannot be touched, cannot be seen, cannot be cut. In fact, like I always say, before you can cut it, you need to touch it. And before you can touch it, you need to define what you mean by touch. And if you have two objects, and here's the big problem, you have two objects, right? You put them together. If they're touching, it's because they became one. Because that means there's no space at all whatsoever between them. They became one object. And so how can you talk about touch between one object? How can one object touch itself? And if there's space between them, then they haven't touched each other. So you got to define touch before you can define cut or rip or break. Okay, so that's the issue. You got to define the word touch, and good luck with that one. You got to look at my book to find out what the word touch means. Long story. Okay. Another comment. Final one, I think. Okay, and here it goes. If I can get this thing. You said in your golden principle of physics require an object, but you not mention particularly that physics requires 2D or 3D objects in your golden principle, and this creates little problem because when we ignore the right 3D in front of object for purpose of physics, then it's like considering human without heart. I think you miss 3D in front of object in your golden principle. Not. Okay. In fact, here we have one fellow out there. I don't agree with him, okay, by the way, but one fellow out there proposes 2D objects. He proposes the 2D ribbons, okay? He says it's not ropes, it's ribbons. And the ribbons, he says, are flat. In other words, are two-dimensional. I don't agree with him, but he's certainly allowed to put 2D ribbons on the screen. Whether that's what happens in real life out there, that's a separate story. I don't think it does, but as you can see, he can propose that. What he cannot propose is that things are made of concepts, which is what mathematical physics proposes. Mathematical physics proposes energy, mass, field, all concepts. They say, oh, we transfer the energy here to there. Oh, we transferred information. What do you mean transferred information? What are you going to transfer next? Money? These words are concepts. You do not transfer money in physics. You do not transfer information. Okay? You do not transfer love. You can only transfer physical objects. What's an object? That which has shape. Does love have shape? Yeah, it has the shape of a heart. Yeah, is that what love looks like, a heart? What does information look like? What does energy look like? What does mass look like? So if you can't visualize these concepts and you cannot give shape to them, then they're not valid in physics. You cannot use them as physical objects for the purposes of physics. And no, we do not need to put 3D in front of objects. We say that objects, because otherwise I would have to also put, because you can't even use 3D objects. See, the table I'm imagining, that's a 3D table, okay? And, that's not a real table. So 3D wouldn't cut it either. Okay, by the way. So no, we do not need to put 3D. We need objects. And that's sufficient. If you propose 2D objects, well, you're going to have to defend your hypothesis, your proposal. If you're going to use mental objects, the ones you imagine, if you want to use tri-bars, no problem. Just make sure you can justify them when you're giving your presentation, your dissertation. If you can't justify them, well, then your theory goes down the drain. But that doesn't rule out the fact that physics just requires objects, something that has shape. We have shape, we have something to look at on the screen. Then you can do whatever you want on the screen. You can move a square from here to there if you want, but you better be able to justify it. That's the issue. Okay, with that, I'll see you on Wednesday, and I'll probably answer some of the other questions. I think a little over time. We'll see you then.